Hi, everyone. Welcome back to freepilotgroundschool.ca, where you get what you pay for. I just figured that would be our new motto or something like that. Anyway, a little bit of history. I started digitizing my ground schools, putting them on YouTube as a COVID project. And unfortunately, I guess for me, I kind of got carried away and then ended up doing preparatory ground instruction. So you can see that as well. And I'm going to start a new series kind of advanced topics. And the reason for this is because, well, I'm a pilot but I also have a bit of an academic background. And one of the things, let's say you have an engineering degree and you start learning to fly, or let's say you're a physicist, all of a sudden you're like, wait a minute, everything that I've learned in my ground school is not really true, or especially the theory of flight portion. The rest of it's true. Sorry. Um, it's probably dumbed down at best, and sometimes it's just misleading. So I decided to call this series the Dumb Pilot series, and there's nothing wrong with that. Kind of reminds me of an old joke. How much? What's the IQ it takes to fly a modern jet? It's 150, and that's why there's two of us. So anyway, we'll get started on this. We'll talk about energy management for dumb pilots, and this will apply to you if you're flying a light aircraft, or let's say you're flying a larger aircraft, and it's all about managing your energy and understanding what that means. Let's get started with some definitions. First off, energy. Energy is the quantitative property that must be transferred to a body to perform work on or heat that body. And measured in joules, that's the SI unit, or the BTU, the British thermal unit. Second, we have power. Power is the rate of doing work. So power equals the work divided by the time. Power is measured in watts, that's the SI unit, or in horsepower. Talk briefly that energy cannot be created or destroyed, only transformed. That's kind of the dumbed down version of the second law of thermodynamics. Here's the actual law of thermodynamics. If you're interested, but you're probably not, I'll quickly explain it to you. The entropy always has to be greater than the heat divided by the temperature. And in case you're wondering, D, that kind of means infinitesimally small. It's used in calculus, and then you see the sigma Q, or sigma heat, which also means the same thing, but they're different. And in case you're kind of geeky like I am, you're like, geez, why are they using a different Greek or a different letter? One's D, one's sigma, to mean essentially the same thing. The reason for that is because entropy is a state function, whereas heat is a path function. You can go on Wikipedia and look that up if you want more information. I'm not going to bore everyone else with that for this lesson. Let's begin with a discussion of the different forms of energy. So first off, we have potential energy. So the height something is above a surface, potential energy is always kind of a difference, uh, a height difference. Obviously, if something's lower, you're dropping something off a mountain onto the ground at sea level, or the mountain into a valley, it's going to have more potential energy. So in an airplane, that's altitude. We can think of a roller coaster when the roller coaster is up top, and the potential energy is mgh. So m is the mass times the gravitational acceleration. That's 9.8 times the height. And I use the form EP. Sometimes you'll see U used as energy, but I just wanted to use E because it's simple. Secondly, we can talk about kinetic energy. In the aircraft sense, it's airspeed square, and the kinetic energy is 1/2 the mass times the velocity squared. And later on in this lesson, you'll come to realize that this square, the fact that it's a power of 2, ends up becoming super important. So both potential energy and kinetic energy, we can also call those two mechanical energy. In an airplane that's flying at a given altitude and a given airspeed, if all of a sudden we pull up, we end up trading kinetic energy for potential energy. Likewise, if we push over, so push down, we're going to trade potential energy for kinetic energy. We'll speed up, but lose potential energy. And in an ideal world, it would be a perfect trade-off. But of course, we don't live in an ideal world. There's heat, there's friction, also drag, things like that. So it's not going to be perfect. Next, we can talk about chemical energy. So we have chemical energy on board the aircraft. That's our fuel. So gasoline has an energy capacity of 46.4 megajoules per kilogram, or 34.2 megajoules per liter. And I did the math on this. This is absolutely huge. That's a massive amount of energy. And you want to know why aircraft use hydrocarbons, such as jet fuel or gasoline. It's because the energy density is just so high. So that amount of energy, that would lift a elephant, the average elephant, 700 meters into the air on 1 liter of gas. Lastly, what we'll talk about, we have thermal energy, so that's heat. So air, for example, has a specific heat capacity of 1 kilojoule per kilogram per degree Kelvin. A degree Kelvin's the same. 1 degree Kelvin equals 1 Celsius, although the scale is offset by 273.15 degrees. So I kind of did a bit of math here as well. That 1 liter of gas that we just talked about will also heat the average 2,000 square foot house by 62 degrees. And again, that's assuming no heat losses. Now we can constantly have these forms of energy trade off against one another. So we already talked about the pull up and the push up. We can also convert chemical energy to potential energy by climbing the aircraft, right? We burn more fuel on a climb. We can burn that chemical energy and get thermal energy out of it. That's combustion. And we can trade kinetic energy for thermal energy, heat. And that would be like a rocket reentry. So when a spacecraft re-enters the atmosphere, it's going to heat up because of friction. It slows down and turns into heat. Now, all of these forms of energy, when they're being traded off within a closed system, have to reach an equilibrium. So they have to equal zero. So the chemical energy that goes in, well, it gets traded for potential energy, kinetic energy. And then eventually it all gets wasted in thermal energy, because by the time we land our aircraft, we just got rid of a whole bunch of gas. We have no more potential energy and no more kinetic energy. So where did that chemical energy go? Well, it got turned into thermal energy and released into the atmosphere. We can do a bit of math now and figure out what the trade-off is between potential energy and kinetic energy for an aircraft. And that potential energy kinetic energy trade-off is 9 feet per knot per 100 knots. So for example, if we're flying along at 100 knots and we pull up until we reach 60 knots, so we reduce it by 40 knots, we are going to gain 360 feet of altitude. And this is one of the reasons why it never looks impressive from the ground when somebody decides to do an abrupt pull-up in their Cessna 150. 360 feet, that's ideal. Plus we have drag. So in reality, it's only like 200 feet. And well, that's just not that much. Another example, let's say an aircraft is an aerobatic aircraft is doing 200 knots, pulls up until they're at 160 knots. So again, they've lost 40 knots. The gain will be 720 feet of altitude, right? Because the trade-off is 9 feet per knot per 100 knots. So if we're at 200 knots, it will be 18 feet per knot. And this is because of the fact that the kinetic energy is the airspeed squared. So the faster we end up going, the more altitude we'll get per knot lost. We can measure energy and power using our instruments. So think of your altimeter. That's an energy instrument. Other energy instruments are the airspeed indicator and fuel quantity. The altimeter tells us our potential energy, or is an indication of our potential energy. Our airspeed indicator is a rough indicator of our kinetic energy, and our fuel quantity gauges are a rough indicator of our chemical energy. Likewise, we can see our power instruments, we'll call them. We have our vertical speed indicator, our tachometer, which is telling us how much power the engine's developing, and the fuel flow is also telling us how much power the engine is developing. Now we have controls in the aircraft. The throttle is the control that allows us to convert chemical energy to mechanical energy, and the elevators allow us to convert kinetic energy to potential energy, and vice versa. Let's discuss how energy changes over flight. So here we have 3 graphs I'm going to develop. One's chemical energy, the second one potential energy, and the third one kinetic energy. So on takeoff, we're going to burn fuel. So our chemical energy that we have on board is going to decrease. We have no potential energy. We're rolling down the runway. But as we're accelerating, we are gaining kinetic energy. Now we lift off and we start to climb. You'll notice the slope of the chemical energy will start reducing because we're not burning quite as much fuel anymore as we're climbing. Our potential energy is increasing, and our kinetic energy will just say that it is remaining constant because our airspeed in a climb is usually constant. Now we're in cruise. You'll notice the slope of chemical energy is decreased some more because we are not burning as much fuel as we were during the climb or takeoff. Our potential energy is constant, and our kinetic energy, after a brief period of acceleration as we level off, remains constant as well. Now we start a descent. Descents usually involve a reduction of power, so we're not burning our gas as fast as we were earlier in the flight. The potential energy decreases, and our kinetic energy, for this sake of argument, we'll say it remains constant. We're going to descend at the same speed we were cruising at. Now we're going to do an approach. We're close to idle, so we're not burning much fuel. Our potential energy continues to drop, but not as at as high of a rate as our descent. And our kinetic energy begins a roughly linear decrease to zero as we touch down and slow down. Some thing for you to be aware of, the slope of the line of the chemical energy is the fuel consumption. So the power equals the change in energy over time. We'll learn a bit more about what that means. The D means it's a derivative. We'll learn a little bit of calculus in the next lesson that I am going to do. Now, in an ideal world, the difference in chemical energy would equal the sum of the potential energy gained and the kinetic energy gained. However, it does not. So where does this excess energy go? Well, recall this heat, everything has to be in equilibrium. So if potential energy and kinetic energy doesn't equal chemical energy, well, it's lost in heat. This is mostly combustion heat from burning fuel, but there's also a bit of skin friction and aerodynamic compression heating involved as well. Now, I've tried my best to teach you guys that are watching a little bit about what I know a fair amount about, but one thing I'm kind of curious of, and this is kind of a digression, so if you want to fast forward, you can. But I have a question that I haven't been able to find the answer to on the internet. So maybe there's somebody who's like an atmospheric physicist that can send me an email. So I'm going to ask a question to somebody in the crowd, and hopefully somebody can answer this question for me. And if you do, you can send me an email with the answer. So I've kind of wondered if the world burns, like humanity burns like 97 million barrels of oil a day, and that puts out a massive amount of heat into the atmosphere. And now I'm familiar with the greenhouse gas effect, but there's also a certain amount of mass in the earth, in the atmosphere. And so that heat has to go somewhere. And of course, some of it's going to radiate out into the atmosphere, into space, but some of it's going to be trapped. And I'm curious if how much of that actual burning contributes to climate change, to global warming. So I know the greenhouse gas effect contributes most of it, but it's like if we were in a house and we just kept burning wood or burning oil in our house, the house would just continue to heat up. So if you know that answer to that question, can you send me an email? Because that would be really interesting to know. So let's discuss how all of this energy management principles that we just learned apply to approach and landing. So a stable approach is a gradual and linear reduction in total energy. As you descend, you're going to reduce your potential energy. And as you slow down, you're reducing your kinetic energy. If you fail to manage this energy reduction, you're going to end up being either too fast or slow, or too high or too low. So for an example, here's a Boeing 777-300. The approach lasts approximately 10 minutes. And during this approach, the pilots have to manage a reduction of approximately 3.7 gigajoules of energy. That's 2.5 gigajoules of potential energy and 1.3 gigajoules of kinetic energy. If there's not enough energy reduction, the aircraft overruns the runway. If there's too much energy reduction, the aircraft lands short. In this case, this was a kind of a side note of Boeing 777 going into Heathrow, and on final, both engines flamed out because of potentially fuel contamination. So they weren't able to convert the chemical energy they had on board into mechanical energy. Here's a little graph. We have potential energy on the y-axis and kinetic energy on the x-axis. If we have too much kinetic energy, so we're too fast, and we have too much potential energy, we're going to be high and fast, and we have to reduce power. If we have too much kinetic energy but not enough potential energy, we're going to be fast but low, so we can just pitch up and trade some of that energy off. If we are too high but too slow, we're high and slow, we can pitch down to trade off some potential energy for kinetic energy. And if we are too low and too slow, we need to add power because we have too little potential energy and too little kinetic energy. And ideally, we just want to be on speed at a proper airspeed and our proper altitude. Now here's something interesting, and I mentioned this earlier. So remember that kinetic energy is a function of airspeed squared. And this is where this becomes pretty important. So roughly, and I know this sounds pretty rough, but being a bit slow is worse than being a bit low. Now we'll explain to you why. Let's assume that we're flying along at 1,000 feet AGL at a constant airspeed. Our potential energy is 305 kilojoules. So remember, potential energy is the mass times the gravitational acceleration times the height. And so if we are a 1,000 kilogram aircraft, 305 meters, we have 305 kilojoules. Now, the aircraft inadvertently descends by 10%. It's now at 900 feet. The potential energy is now 274 kilojoules, so we have a 10% reduction in potential energy. Now let's look at the kinetic energy. We're flying along at 100 knots, the same aircraft that's 1,000 kilograms. Our kinetic energy is 1.3 megajoules. So remember, kinetic energy is half the mass times the velocity squared. We inadvertently slow down by 10%. We're now flying at an airspeed of 90 knots. Our kinetic energy is 1.07 megajoules. That's a 17% reduction in kinetic energy. If we want to get this energy back, we're going to have to add considerably more power than we do if we just need to make sure that we don't fly too low. Here's a second application of energy management, the forced approach. So during a forced approach, you either have no more chemical energy, no more fuel, or you don't have access to an engine that will convert your chemical energy to mechanical energy. Now, instead of the throttle to manage the trade-off between chemical energy and mechanical energy, we have to manage the reduction in energy with drag. We can use this by using flaps, side slip, but remember, we can only reduce the energy. We have no way to add energy into the system. Diving also rarely works because what ends up happening is you generally just trade off altitude for speed. So you haven't really reduced your energy much. You do a bit because diving makes you less efficient, but it's not nearly as effective as flaps or a side slip. Failure to reduce your energy fast enough during a forced approach results in you overflying your landing area. Conversely, reducing your energy too fast or having insufficient energy to begin with, you're too low for your gliding distance, results in being too short to make up the landing area. That concludes my lesson for today. Thanks a lot for watching. I'm going to have another video posted pretty soon on YouTube talking about aerodynamics. Fly safe and enjoy the ground school videos.